Welcome to this explainer. Today, we are taking a massive evolutionary journey. We're looking at how artificial intelligence in software engineering is rapidly mutating from simple, one-off AI code generation into massive, highly structured autonomous systems. We're going to break down the exact architecture that takes us from a single AI loop all the way up to thousands of agents working together seamlessly.
Okay, let's dive into this with a quote from AI researcher Andrej Karpathy. He envisions a future of autonomous swarms of AI agents running across compute cluster megastructures in the skies. I mean, that is an incredibly cinematic vision, right? It immediately hooks you on the sheer scale and ambition of frontier AI research right now. We aren't just talking about a chatbot writing a quick Python script anymore. We're talking about building entire virtual research communities. So, how do we actually get there?
And frankly, this scale is not science fiction. Anthropic's dynamic workflows are already proving this out. In fact, their system is capable of spawning up to 1,000 fresh context parallel subagents from a single prompt. Think about that number for a second. 1,000 independent agents, all spinning up to tackle complex parts of a problem simultaneously. If you've ever been in a group project with just 4 people, you know exactly how messy that gets. So how do you actually orchestrate 1,000 agents without complete chaos?
Well, here is our roadmap for the explainer. 1. Beyond vibe coding. 2. The auto research ratchet loop. 3. Scaling up to swarms. 4. The knowledge graph memory. And 5. Building the agentic system.
All right, let's start with Section 1, Beyond Vibe Coding.
To really understand where we're going, we have to establish our baseline. Just look at this evolution. We started with Software 1.0, where humans manually typed out explicit, line-by-line instructions. Then came Software 2.0, where behavior was shaped by data and neural network training. More recently, we entered the era of vibe coding, where you essentially express a natural language intent and the AI model writes the code. But here is the core problem. Vibe coding completely breaks down when you need an AI to run complex, multi-step experiments. You can't just dump a massive project history into a simple chat transcript. The context window gets bloated, the model loses track of what's important, and everything just falls apart. That's exactly why we moved to agentic engineering, where humans orchestrate and verify, and ultimately to graph engineering, where agents share a durable, queryable state.
Moving right along to Section 2, the Auto Research Ratchet Loop.
This right here is the first vital evolutionary leap that bounds the AI agent in a controlled, safe environment. This loop actually comes from Andrej Karpathy's Auto Research repository, and it's a brilliant, narrow design choice. The agent is placed inside an executable research harness and asked to make just one single change at a time. It proposes a change, applies and commits it, and then runs a fast 5-minute training run to evaluate the metric. If the metric improves, awesome, it keeps the commit. If it crashes or the metric gets worse, it mechanically reverts back to the last good state. This one-way ratchet fundamentally externalizes the evaluation step, rigorously protecting your codebase from AI hallucinations, because every single change is grounded in a verifiable test.
Now, what's really interesting about this slide is the sheer output mapped out here. The core code for this harness is tiny. We're talking roughly 630 lines. But over just 2 days, this bounded loop allowed an agent to autonomously run about 700 experiments. And it independently discovered around 20 real useful optimizations, things like AtomW parameter tuning and batch size changes. It systematically explored narrow paths and built a machine-readable history of hypotheses and failures, all without a human holding its hand.
Which brings us to Section 3, Scaling Up to Swarms.
So how do thousands of these agents work together without stepping all over each other's toes? Well, to emulate a research community, we need an agent-first platform. Enter Agent Hub. This architecture totally inverts our human assumptions about Git. For us humans, Git is all about converging on a single truth. We use pull requests, merge queues, and a main branch. Agent Hub drops all of that, the whole shebang. It uses a bare Git repository on disk, a simple SQLite database, and a message board where agents can post their hypotheses. By dropping the main branch, it allows a swarm of agents to traverse a massive search graph of experiments simultaneously, exploring thousands of dead ends and breakthroughs at the exact same time. As you scale this up, you absolutely have to separate how you track work from how you track facts. The commit DAG, or directed acyclic graph, acts as a family tree of experiments. It answers the question what changed and tracks the lineage of parent commits. But alongside that, you need a knowledge graph. This acts as the domain memory. It answers which entities exist and tracks the relationships and evidence that actually support specific claims. These two structures are completely complementary, and they prevent your agents from having to rebuild the world from scratch every single time they spin up.
Let's dig deeper into that memory aspect in Section 4, the knowledge graph memory.
This is really the climax of this entire evolutionary architecture. Think of the shared memory layer as a massive, persistent, long-term hard drive for your swarm. Instead of taking every single worker's chat transcript and pasting it into a master orchestrator's prompt, which, let's be real, would blow up your token limits instantly, the agents write their findings as structured updates to a graph. This graph serves as a persistent world model.
And this brilliantly illustrates exactly what we mean. Notice the central agent node here. Instead of just relying on free-flowing text, it connects to typed entities through directional edges. It points to specific tools, specific people, or specific metrics. It provides a highly structured queryable reality for the swarm. When an agent needs information, it doesn't have to read a massive, bloated summary. It simply queries the relevant edges of this graph to retrieve the exact task-specific state it needs to make a decision.
Anthropic relies on this exact architecture across multiple patterns. In prompt chaining, the graph is a gate signal to check entities. In parallelization, it acts as a shared surface where workers publish their non-overlapping findings. For orchestrator workers, it's the shared memory that keeps the central orchestrator's prompt totally clean. And perhaps most importantly, in an evaluator-optimizer loop, the graph acts as a grounding layer. An evaluator can check an agent's claims directly against the cited edges in the graph to ensure they are based on actual cited evidence, not just AI hallucinations.
All right, let's bring it all together in Section 5, Building the Agentic System.
Let's move to and see how this builds out in reality. Because here is a practical, step-by-step roadmap for building your own scalable system. You don't just magically start with 1,000 agents on day one. On day one, you build a simple reflective loop, kind of like auto research, just to measure quality improvement. Day 2, you add specific tools to fix known errors. By week 1, you introduce JSON planning. In week 2, you finally split into multi-agent specialized roles, like having a separate coder and a reviewer. By month 1, you wire this into a persistent graph so knowledge actually survives between sessions. And finally, by month 2, you scale to that massive parallel swarm workflow. You only ever add complexity to solve a specific system bottleneck. To safely run this at scale, a reference production architecture rigorously separates the system into these 5 distinct planes. The control plane manages budgets. The execution plane runs the isolated agents. The artifact plane stores immutable drafts. The graph plane handles entities and provenance. And the evaluation plane runs the checks. Rigorously separating these is absolutely crucial. Why? Because you literally must ensure that a single messy chat transcript doesn't accidentally become your entire database, your workflow engine, and your audit log all rolled into one. That's a recipe for disaster.
Ultimately, graph engineering is about moving from volatile memory to durable memory, and from estimation to hard evidence. So I want to leave you with this question, to assess your own workflows. Can your AI's output be traced back to an explicit source, a specific graph path, and a bounded execution record? If the answer is no, well, adding more agents will only increase the opacity and chaos of your system. But if it's yes, you are well on your way to building truly autonomous, reliable swarms. Thanks for joining this explainer, and we'll see you in the next one.